Welcome to Semiconductor Career Landscape. This series presents the semiconductor industry as an interconnected engineering system rather than a collection of isolated job titles. We will move from chip architecture and design through devices, process technology, manufacturing, packaging, product engineering, factory operations, software, data, EDA, and customer-facing roles. The goal is practical to help you recognize where your existing strengths can contribute and where additional learning can open new options. You do not need to choose a permanent career path while watching. Use the map to identify engineering problems that genuinely interest you, then investigate them with greater depth. This deck is evidence-based, but it is important to distinguish evidence from organization. Company-specific role descriptions, technical responsibilities, and stated requirements come from publicly available company materials. The 7 World 35 Mission Taxonomy is an educational synthesis created to make those materials easier to compare across the industry. No confidential company information is used. The framework is therefore not presented as an official taxonomy adopted by the companies themselves. Think of it as a navigation system. The source facts remain traceable to public material, while the structure helps us see recurring engineering responsibilities that may appear under different titles. The course is organized in 5 stages. We begin with the overall landscape, then examine the 35 engineering missions in detail. After that, we learn how to read a product such as HBM as a network of engineering decisions, compare how different company types emphasize different missions, and finally connect academic backgrounds to possible career directions and evidence-building strategies. This sequence matters. Starting with job titles can be confusing because titles vary widely. Starting with engineering ownership gives us a more stable reference. By the end, you should be able to read a job posting and ask a more useful question: what problem is this role actually responsible for solving? Part 1 establishes the map before we enter individual missions. The semiconductor industry is much larger than chip design alone, and a useful career framework must include the work required to manufacture, package, qualify, operate, and support a product. In the next few slides, focus on the life cycle rather than on specific employers. The central idea is that a successful semiconductor product is the result of many specialized engineering communities handing trustworthy outputs to one another. Once that life cycle is clear, the individual career missions become easier to understand because each one has a recognizable place in the larger system. When people first encounter semiconductor careers, they often see the most visible roles: circuit design, process engineering, or perhaps verification. The actual industry is much broader. A product also depends on metrology, inspection, equipment, packaging, test, yield, reliability, failure analysis, factory operations, software, data, EDA, design enablement, and customer engineering. This breadth is encouraging because it means semiconductor careers are not limited to one academic profile. Electrical engineering is important, but so are physics, chemistry, materials, mechanical engineering, computer science, industrial engineering, mathematics, and data science. The key is to connect each background to a real engineering responsibility. Use this career map by following ownership. For any mission, ask 4 questions. What problem does the engineer own? What output must be delivered? What workflow produces that output, and which neighboring teams depend on it? This approach is more reliable than memorizing titles because titles are company-specific. An applications engineer, for example, can mean something very different from a product engineer, even though both may work closely with customers or silicon. The mission framework gives you a stable reference for comparison. As you explore roles, pay attention to the boundary statements. They are there to clarify where one responsibility ends and another begins. Here is the complete landscape: 7 engineering worlds containing 35 missions. The numbers are identifiers, not rankings. World 1 covers chip design, World 2 devices and process development, World 3 manufacturing technology, World 4 system integration through advanced packaging, World 5 the conversion of silicon into a qualified product, World 6 factory operation, and World 7 the digital and customer-facing layer. Some careers sit near the center of one world, while others collaborate across several. The value of the map is not perfect separation. Its value is giving us enough structure to understand how specialized engineering work connects across the semiconductor life cycle. Part 2 is the technical core of the course. We will now move through all 35 missions. For each one, listen for the engineering question rather than trying to memorize every bullet. Ask what success looks like in that role and what evidence would convince another engineer that the work was done well. The missions are intentionally described through outputs, workflows, metrics, and boundaries because those elements travel better across companies than titles do. If a mission catches your attention, note the neighboring roles as well. Semiconductor careers are highly collaborative, and understanding those interfaces is often as important as understanding the mission itself. World 1 brings together the missions that define and prove the chip before manufacturing begins. Architecture establishes the system intent, RTL and circuit design implement it. Physical design turns logic into manufacturable geometry verification challenges. Functional correctness, and DFT prepares the design for production test. These are different careers, but they form one continuous chain of responsibility. A useful way to explore this world is to ask where you most enjoy making decisions defining the system, building the implementation, proving correctness, or preparing the design for manufacturing. None of those choices is inherently more advanced than another. They require different forms of depth, and modern semiconductor teams depend on all of them. Architecture is where a chip begins as a set of choices rather than a collection of RTL blocks. The architect decides what the product must accomplish, which functions belong in hardware or software, how memory and interfaces are organized, and which performance, power, area, cost, and reliability targets matter most. Those decisions become constraints for every team that follows. A strong architecture, therefore, does more than look elegant on a block diagram. It gives implementation teams a target they can actually close. For someone drawn to this work, breadth matters. Digital design is important, but so are memory systems, workloads, software behavior, and the ability to reason about trade-offs before implementation begins. RTL design turns architectural intent into cycle-by-cycle hardware behavior. That sounds straightforward, but the real engineering challenge is precision protocols must be correct, pipelines must meet throughput goals, resets and corner cases must be safe, and the structure must remain synthesizable and verifiable. Good RTL engineers think beyond writing Verilog or system Verilog. They understand how a coding decision affects timing, area, power, verification complexity, and downstream physical implementation. A useful portfolio project therefore shows more than a module that simulates correctly. It shows clean interfaces, assertions or tests, synthesis results, and an explanation of the design choices that made the implementation robust. Analog, mixed signal, and RF design occupies a different design space from digital logic. Here, transistor behavior, noise, linearity, matching, stability, bandwidth, and process variation are part of the function itself. An ADC, PLL, SerDes front-end, or RF block cannot be judged only by whether a logical output is correct. Its quality is measured through continuous electrical behavior and carefully defined figures of merit. This mission rewards a strong foundation in circuits and devices, but it also rewards disciplined modeling and verification. The most convincing student evidence is therefore a complete chain from specification to schematic-level design, simulation across corners, and a clear account of the trade-offs that shaped the final circuit. Physical design is where a logical netlist becomes manufacturable geometry. The central challenge is closure timing, power delivery, congestion, signal integrity, design rules, and area all interact, so improving one dimension can make another worse. This is why physical implementation is not simply an automated push-button step. Engineers interpret reports, identify the real limiter, adjust constraints or structure, and repeatedly converge toward sign-off. Students interested in this mission should become comfortable reading timing paths, floor plans, utilization maps, and power results rather than focusing only on tool commands. The transferable skill is the ability to explain why a design failed to close and what engineering change resolved the problem. Design verification asks a deceptively simple question: does the design behave correctly under every condition that matters? The difficulty is that modern chips contain too many states and interactions to test by intuition alone. Verification engineers therefore build environments that generate meaningful scenarios, check expected behavior automatically, measure coverage, and expose corner cases before silicon exists. The work combines hardware understanding with software discipline and statistical thinking. A strong verification project demonstrates not only that tests passed, but that the test plan was systematic, coverage gaps were understood, and failures could be reproduced and diagnosed. That ability to turn uncertainty into evidence is what makes verification indispensable. Design for test engineering prepares a chip to be tested efficiently after fabrication. Internal faults are not directly visible at package pins, so DFT engineers add structures such as scan chains, memory self-test, compression, and test access mechanisms that make manufacturing defects observable and diagnosable. The mission sits at an important boundary between design and production choices made before tape-outs strongly affect test time, fault coverage, yield learning, and failure diagnosis later. For students, the most valuable evidence is not simply inserting scan logic. It is showing the relationship among fault models, coverage, pattern count, test cost, and diagnosis, and explaining how test data can feed back into yield improvement. World 2 moves from circuit intent into the physics and chemistry of fabrication. Device engineers define transistor behavior process integration coordinates, the complete flow unit. Process engineers develop individual steps, and materials engineers control the substances and interfaces from which the technology is built. The important idea is interdependence. A transistor target cannot be separated from the process sequence that creates it, and a process cannot be separated from the materials and equipment that make it possible. Students from physics, chemistry, materials, electrical, and mechanical backgrounds can all find meaningful entry points here. The common language is experimental evidence-measured behavior, controlled variation, and a clear link between physical cause and manufacturing outcome. Device engineering focuses on the transistor and device structures that ultimately determine what a technology can deliver. Engineers connect physical mechanisms, electrostatics, transport, leakage, variability, reliability to measurable device characteristics and technology targets. As dimensions shrink and structures become more three-dimensional, this work increasingly depends on simulation, characterization, and careful interpretation of process effects. It is a natural home for people who enjoy semiconductor physics, but also want their analysis to influence real products. A strong project might compare device structures, extract parameters from measured or simulated curves, or show how a physical change affects performance, leakage, and reliability simultaneously. Process integration owns the complete manufacturing flow rather than a single process step. The challenge is that deposition, lithography, etch, implant, clean, anneal, and planarization interact. A change that improves one module can damage another or shift the final device characteristics. Integration engineers therefore define baseline flows, design split experiments, correlate electrical and physical data, establish a stable process window, qualify the technology, and transfer it into high-volume manufacturing. This mission is especially suited to engineers who enjoy systems thinking at the process level. The strongest evidence shows how multiple process variables were connected to final device or yield outcomes, not merely how one unit process was optimized in isolation. Unit process development goes deep into one manufacturing operation such as etch, deposition, diffusion, implantation, CMP, or cleaning, and asks how to create a repeatable process window that meets the integration target. The engineer must understand equipment physics, materials interactions, chamber conditions, metrology, and statistical variation. The goal is not the most impressive single wafer result. It is a process that remains stable across wafers, lots, tools, and time. Students can demonstrate this mindset through designed experiments, response surface analysis, or process window studies that distinguish sensitivity from robustness. That distinction between a good result and a manufacturable process is central to semiconductor engineering. Materials engineering examines what the semiconductor is physically made from and how those materials behave during fabrication and operation. Thin films, dielectrics, metals, polymers, underfills, substrates, and interface layers all introduce questions of adhesion, diffusion, stress, contamination, thermal expansion, and long-term stability. As devices and packages become more heterogeneous, materials choices increasingly affect electrical performance and mechanical reliability at the same time. This mission is therefore broader than materials selection. It requires linking composition and microstructure to process compatibility and product behavior. A strong student project connects characterization data to an engineering decision. For example, why one material stack improves reliability, but creates a new process or thermal constraint.